Hi, everyone. If you like the way I teach and want me to be your teacher, the link to my engineering fundamental school is in the description below. Enjoy the video. Today we'll be going over a 3D particle equilibrium problem, which brings together a lot of the concepts that we learned describing three-dimensional vectors and equilibrium in general. Let's go ahead and draw the problem diagram, which is an inclined plane in three-dimensional space. On this surface of this inclined plane, we have a particle. This particle is connected to two cables, cable B and cable C. The coordinates of A and C are given, while the angles relative to B are given. Our goal is to find the tensions in the cable as well as the normal force. Knowing that the weight of the particle A is 200 pounds, we can also see the slope of the inclined plane was given to be 7 rise and 24 run. I'm going to give you guys an opportunity to try the problem on your own. Okay, I hope you tried the problem. What we're going to start off with first is drawing the free body diagram. So let's go ahead and do that. We see those two tensile forces in the cable. We're also going to place the weight and the normal force. And that's the complete free body diagram. Now, of course, our equation is Newton's second law, assuming static equilibrium. What we're writing in this first line here is that the sum of the forces must be equal to 0. What are the forces acting on the free body? The two tensions, the normal force, and the weight. Now what we need to do is be able to describe these vectors in Cartesian form. That starts off with finding unit vectors. Let's find the first unit vector, lambda hat AB. If we draw the projection of that blue line in the YH plane, connecting B and the axis H, if we assume that that line has a length of 1, then we can be able to find our unit vector components. We know that the bottom side, that FH projection in the horizontal plane, is the sine components. And we simply have to break that down to find the x component, which is a sine of 60 of that, and the z component, which is the cosine of 60 of that. And the y component is just that vertical component. That's the cosine 30 component. What we have to do is make sure we have the signs correctly. So let's start at particle A. We know we have to move left, corresponding to a negative on the x. We know we have to move in, corresponding to a negative on the z. And for the y, we move up, which means we have a positive sign there. Let's go ahead and reduce this lambda hat AB term. We can also verify that its magnitude is 1, which it is. Let's go ahead and move on to lambda hat AC, which can be found by taking the full position vector and dividing off by its length. What is the position vector AC? If we think about what kind of sum would give us AC, we know that RA, shown on screen, plus RAC is going to be equal to RC. If we rearrange that equation, we'll be able to get the following difference, that RAC is equal to RC minus RA. Let's go ahead and fill in that information. RC is given by the coordinates value, and RA is also given by the coordinate values. Let's go ahead and take that difference and divide by the magnitude of RAC. If you're enjoying the video so far, please leave a like and subscribe, as it helps me out a lot. The next thing we need to do is explore the normal force unit vector direction. Let's go ahead and draw another view. If we observe the YZ plane, so we can take advantage of the slope that we were given, we know that the rise is 7 and the run is 24. We can write down that slope, which is a negative 7 over 24. If we want to find the perpendicular slope to this given line, all we have to do is take the negative reciprocal of that slope, which is 24 over 7. How could this be written in vector form? We know this is 7 in the k plus 24 in the j. If we divide off by its length, we can get the unit vector in the normal direction, shown here. And the weight is just pointing straight down. It's 200 pounds. Let's go ahead and fill in our equation, where we have Newton's second law with the static equilibrium assumption. Let's go ahead and put that tension AB, the tension AC, the normal force, and the weight. We know all the directions here, so let's fill in all of that information. What we could do is project this equation in 3 directions, which is how we would solve. If we projected it in the I direction, all the j and k components would fall out, and we'd end up with this first equation. We could do this 2 more times for the j and k components, and we'd end up with 3 equations that we can solve using substitution or elimination. What I'm going to do here is take advantage of my calculator. I'm going to write this equation instead in matrix form. So let's get rid of this. If you observe, the top row of the matrix will just be the leading coefficients of that first vector. The second component of that vector will be the middle equation, and the third equation will be the last components. The vector that we're multiplying is tension AB, tension AC, and the normal force. And the x and z components are equal to 0, while the y component is equal to 200 if we move it to the other side. This equation has the form ax equal to b, where a is a matrix, b is a vector, and x is a vector. If we take the inverse of a and multiply it on the left side of this equation, then what we get is this. And our solution is 53 pounds, 45 pounds, and 126 pounds. The tension 1 is the tension AB. The tension 2 is the tension AC. And the normal force is the last thing, 126 pounds, shown on the bottom. I hope this video was a good practice for you, where you got to use some of those 3D vector descriptions that we discussed before in an actual equilibrium problem. Keep learning and keep working hard. Goodbye.